Hello, welcome back to the lab. Welcome back to EEforEveryone. We have a great video for you today. We're going to be continuing on our journey with comparators. We're talking about real comparators today. We're no longer living in the ideal world. We're going to talk about real comparators, and we're going to do some circuit analysis with that. Okay, let's dive in. So we brought up a lot of the characteristics of comparators in our ideal comparators video. If you haven't seen that, check it out. There should be a card up there. But basically, we're going to draw one of these guys real big. So you can see it's kind of simplified. Basically, I'm showing that we've got an input voltage that's got a push-pull output stage. Just let me change some color here. You know what? That input offset voltage, it's really not drawn right. Can I like select? Whatever. So if I really wanted to draw that input offset voltage more accurately, what I would need to do is I need to put it in series here. So we would actually put it, right here and right here. But you kind of get the point. We've got our output, we've got our power in, we've got our reference, we've got our positive terminal, we've got our negative terminal of the comparator. Okay, so we've got some bias voltage, and this is basically the amount of voltage that is required to exceed. So normally these would trigger this second, the instant 0.0001 millivolts of the positive input being above the negative or vice versa. But that bias voltage, maybe it needs 100 millivolts, maybe it needs 10 millivolts, maybe it needs 5 millivolts, maybe it needs some amount of voltage to exceed the other input before it'll actually change state. And there's those bias currents, which is maybe you need to source some current into the input of that comparator. That's not ideal, right? If you've got resistors coming in, you'd want that to be a perfect high impedance, but what if it's not quite? What if there's a little bit of current leaking in? Likewise on the output, normally we would assume that it's V in or V out, but it's not quite. So there's something called VOL and VOH, which is the low and high output voltage. V out low and V out high, that's what that stands for. So basically, it's saying how close can we get to V in, how close can we get to ground, how close can we get to our reference. Those are really the non-ideal parameters that we're going to be walking through today. And let's just look at how that looks in a circuit. So let's consider this circuit. Okay. We have a very simple ideal voltage reference. This is going to be set to 1 volt. We're going to bring that into our negative terminal. We're going to supply 5 volts to the positive input, or to the supply input. All grounds are tied together. Got a 1 kilo ohm resistor. Actually, we're going to make that a 10K. Here's what we have. V in. So we're going to call this V in, or VI. All right. The big question that we want to answer is, what is V trip? That is, what voltage does VI need to be to make the output change state? And let's think about that for a moment. So the critical node is this one. When this is exceeding or falling off below 1 volt, whenever that transitions around a volt, that's when this is going to happen. And just so you guys know, this is a pretty simple comparator circuit with hysteresis. This is the hysteresis resistor. It's basically going to tweak our trip threshold just a little bit. Prevents some oscillations. Okay, so let's think about the equivalent circuit that we have here. We have essentially a voltage source. This is VO. That's this voltage. And we've got a 10K resistor. Oh boy. I just realized my pen is still big. There we go. And then we have VN. Then that's got a $1K and a 1K. Beautiful. And then there is an additional resistor coming off of this node right here. And then where is that node? This node right here is the critical one. This node is node plus. That's what we're going to call that. It's our positive terminal of the comparator. Okay. That looks really weird, right? These two circuits look very, very different. This doesn't look anything like that. Where did the comparator go? This is obviously a simplified model. This is not a perfect model of our comparator. But it will allow us to consider some non-ideal characteristics of this comparator. What do I mean by that? What do I mean by that? Well, let's say V out isn't quite exactly 5 volts. We can plug in 4 point whatever volts. Maybe there's 100 millivolts of burden. So I'm basically saying that there's 100 millivolts, so the logic 0 state would be 100 millivolts, and the logic high state would be 5.9. Okay, that wouldn't be a great comparator, but that's, that's pretty reasonable. You'd still pretty much see what you'd expect to see. You put a DMM on it, you'd see around 0 or around 5. You would understand most circuits would be able to function with that. But that'll tweak your threshold back here. Whether or not this node is 4.9 or 5.0 volts, that might matter depending on the accuracy of the threshold that you're trying to set. So basically what I'm trying to model here is a way that we can account for all of those non-ideal circuit parameters, all the non-ideal aspects of this comparator. Speaking of, I didn't account for everything. Because at this same node right here, there's a current source. That's our input bias current. So it's possible that we might be injecting some current back into that node. But what's weird about bias currents is they can actually be bidirectional. So we could be sourcing or sinking current from that node. Okay. And the offset voltage would basically be a 1-for-1 shift of whether it's tripping at 1 or 0.9 or 1.1 or whatever it would need to be for this particular comparator. Okay. So let's try to consider this model and do some calculation with it to find V trip. Let's apply what we've just learned about Kirchhoff's laws and building node equations and mesh equations. And yeah, we've got a current source, we've got some voltage sources, we've got some resistors. Let's see what we can do. I've gone ahead and saved you the trouble of needing to watch me redraw this, but what we need to do is we need to add some numbers to this situation. So V out is going to equal 4.9 volts or 0.1 volts, depending on the state. And it's 4.9 volts when V plus, the voltage of that node right there, V plus is greater than 1 volt plus input, what did we call it? We called it input offset voltage, which is really weird. It should be VIO. We're going to call it that. Plus VIO. So basically I'm saying we need to get above 1 volt plus that input offset voltage to be 4.9 volts. And we need V plus to be less than 1 volt minus VIO. So basically we need this to be greater than 1 volt plus the input offset or less than 1 volt minus the input offset for this to change state. Okay, so it looks like we're going to need to solve this equation 2 ways, right? We're going to need to find the rising and the falling edge. Okay. And then input offset, here's our input bias current. We're going to say that's equal to 10 milliamps, but that's plus or minus. Plus or minus 10 milliamps. So that means if we really want to account for input bias current, we're going to need to solve for that 2 ways. We've got 2 different numbers to plug in, but it's fundamentally the same math. It's just a matter of whether we're sinking or sourcing current. And then of course, this is what we're trying to solve for. What are those critical thresholds? So let's first solve for V in rising. So that would be transitioning from output low to output high. Now there's 2 ways that we can do this. We can either do this by solving using node or mesh analysis, and then plugging in some numbers and showing the power of a math calculations workbook, or we could do it the hard way and calculate the same thing 4 times. So let's do the first one. Let's show you how this thing works. Okay, so we need to label some other nodes because I'm going to use nodal analysis. We're going to call this node 1. Yeah, that's all we need to label. So we got V plus, node 1. Those node names make total sense, but honestly, doesn't really matter. So our goal is to find V in rising. Okay. So thinking back to what we did a few episodes ago, we need to set up these equations. So this will be, need to add in some arrows. Yep. Okay. We should be all set. So now we've got V node 1 minus V in divided by 1k plus V node 1 minus V plus divided by 1k plus V node 1 divided by 1k equals 0. Those are all the currents around node 1. Great. Let's build our second equation. Now we've got the opposite, so now we've got V node 1, opposite direction. There we go. So now we're going to be doing these three. So the tip of the arrow, the point of the arrow, is the term that we're putting first in these equations. That's what we've decided to do. Again, it's important that you stay consistent. It's not important which way you do it. Because if you're inconsistent, you'll probably end up with the right answer, but with the opposite sign, and you'll feel pretty silly. You also might get the wrong answer and the wrong sign. So be careful. Be careful. So do the voltage at node 1 minus V plus divided by 1k plus so this is going to be IB, since this is a current source, plus and so a positive current direction for IB will be towards ground. That's basically what we just decided. Which means that we need to draw this a little better. We are going to draw this with a more pronounced arrow. Actually, we can just use a different color. There we go. IB. That is the direction of IB. Plus VO minus V plus divided by 10k equals 0. Excellent. Now, combining the partial fractions on the upper one is going to be really easy because they've all got the same denominator. Almost like somebody did that on purpose. But that bottom one's a little bit trickier, but even so, that won't be too bad. All right, let's get these mixed around. Okay, I had to plug these equations into our lovely friend Wolfram Alpha. I went through a couple iterations and I finally got my head around this the right way. Here's what we did. We took this first equation and we solved this equation for, the input voltage, VI. Because this is the only equation with VI as a term. And that's what we want to solve for. So it's important that we solve one of our equations for that. And actually our three 1K resistors all cancel out of this equation. And this is a unitless 3 that made it out. So we end up with a unitless 3 times N1 minus V plus. N1 V plus. So V plus is known, that's fine. We can leave that as a variable. But Vn1, that's not known, that's not fixed. So we need to use our second equation to solve for Vn1. Unfortunately, that was not quite so simple. And solving that turned into this disgusting polynomial right here. And then what we did is we plugged in this for Vn1, combined the two equations, and boom, we've got something that we can work with. Okay, but what is the point, you might be asking? Oh, I'm so glad that you asked. This is that amalgam. This is that equation. You can see that it's a function. We get Vi, Vin. That is our input. Let me go back to our drawing. Vi, that's right here. That's what we're solving for. That is the trip voltage on the input as a function of the positive input, the voltage at the positive input of our op-amp, comparator, symbol is the same, function is very, very different. The output voltage, which is, VOH or VOL, depending on the state, and then the input bias current. Then what we do is we define some variables. So this is our input offset voltage, 10 millivolts. That's what we have that set to right now. And then we calculate the maximum and minimum reference voltage. So basically, if we know we've got an ideal 1 volt reference, it might be triggering at anywhere 10 millivolts above or below that. That's the tolerance. And then we know that VOL at a maximum is 0.1 volts because that's the datasheet spec for that part, but the minimum is actually 0. I mean, if there's really no current coming out, it might be really, really close to 0, so we should account for that. Likewise on VOH, the max is 5 volts, that's our source voltage, but the minimum, as specified by the datasheet for this theoretical comparator, is 4.9 volts. So that is the range, that's the amount of variance that we might see. Then of course, we've got input bias current, which this actually broke the calculation. I thought I made a mistake. Turns out I was just confused. So we said 10 milliamps. Yeah, that's silly because there isn't 10 milliamps to steal. There is not 10 milliamps, so it ended up with negative resistors, negative voltages that we need to apply to make this work out. Yeah, so we're gonna make that a much smaller number. In this case, it was 0.01 milliamps, which demonstrates the point. And then of course, we got all our mins and maxes. So what was the purpose of applying nodal analysis to find these equations? It's right here. Because now when it comes time to actually figure out how the system will behave, it becomes trivial. We use this equation that we derived based on the system, based on our node equations. We calculate the coefficients, or not calculate, but we find everything we need to know, the mins and maxes for all of those variables, and then you just plug them in. So then we can use that equation that we've defined to just say, hey, I want to know what the input trigger threshold is. VI, what voltage will this comparator trip at? That's what we're basically asking. And it says, okay, on the rising edge, so when VOL, assuming this is push-pull, when VOL is when the bias current, the input offset voltage, and the output VOL, VOH tolerance all line up in the worst possible way. Our lowest possible rising edge trip voltage is 2.217 volts, and our maximum is 2.353. Okay? And then once we've triggered, once that output has changed states up to 5 volts, what we see is that our falling edge threshold ranges between 0.883 and 0.747 volts. Now let's say, for example, let's say you have a slightly different op-amp. Comparator, it's a comparator. My mind, yikes. Anyways, so let's say you have a different device that has a different input offset voltage, and you're like, okay, what if it was 50 millivolts instead? You can plug that into your spreadsheet, and immediately that flows down into your thresholds. You can see the impact that has, and you're like, okay, well, what if we get a cheaper comparator that has more bias current? And let's say that goes up by a factor of 4. What would that do to our system? Wow, that has a pretty big impact. That shifts things around quite a lot. So you can kind of play with these things, right? You can play with what happens if our V out high voltage is a little bit looser, and The Vout low voltage is asymmetrical. You can play with all of these types of scenarios so that you can do the hard work the right number of times once. That's really what a lot of this comes down to. You know, we really could have just gone through and done a basic circuit analysis. We could have walked through this circuit analysis and simply calculated it for fixed values of all of these parameters. But now if we want to change this from 5 volts to 3.3, we need to start all over. We need to start all over instead of just changing a number. And that's not very efficient. That's not what you want to do. So that is how we can accommodate the non-ideal parameters of a comparator, build that into a simple kind of circuit, and find the tolerances for all these things. That's pretty cool. If you want to dive into what we did here, I'm going to put the SMath worksheet on the Google Drive so you guys can grab that. Link should be in the description. We'll put some resources down there in general, but I hope that you enjoyed our video today. I certainly had a lot of fun walking through this, and I hope you did too. If you like this video and you can't wait for more, let me know by getting subscribed, hitting that like button, and leaving a comment down below. Coming up soon, we will be applying this to a maybe familiar design example with comparators. That is a latching fault trigger circuit thing. It's going to be a lot of fun. I can't wait. If you want to support the channel, consider checking out our Patreon page linked in the description. It really helps us out a lot. Thank you. Thank you to everyone who has decided to become a member. I appreciate you. Most of all, I hope that you learned something great today, and I hope to see you again soon. So thanks for watching EEforEveryone, and thank you for staying till the end. Bye.